In this lesson, we are going to talk about the fuel utilization. So remember from the oxidative phosphorylation, we said we can break down carbohydrates, proteins, and fats to use them as a fuel for the oxidative phosphorylation. So here we are going to talk about this. The first step in the process of oxidative phosphorylation is the preparation of the compounds. In that case, this compound can be carbohydrates, proteins, or fats for aerobic metabolism. After acetyl-CoA is formed, the Krebs and electron transport chain are the same among the three macronutrients. So, for the glycolysis energy system, we just use glucose or glycogen, which is a carbohydrate. But after we get to acetyl-CoA, that's gonna be the same, like the chemical reactions, the chemical steps after Krebs and electron transport chain are gonna be the same among fats, proteins, and carbohydrates. So here is in the previous lessons, we talked about the oxidation of carbohydrates, but let's talk about the oxidation of fats. We are going to talk about the fats in a separate chapter, but here, let's talk about the fatty acids. The fatty acids are a long chain of carbons. And we have different number of carbon atoms in the chemical structure of fatty acids. Some fatty acids contain 16 carbons, like palmitate, or 18 carbons, like stearate, like or oleic acid. That's another fatty acid. We have linoleic acid, linoleic acid. These are all fatty acids, and they have different, like they produce different numbers of ATPs depending on their number of carbon atoms in their structures. But here, for example, we have palmitate and stearate. Palmitate is 16 carbons, and the stearate is 18 carbons. And the palmitate is one of the most widely distributed fatty acids found in food and in stored body fat. Both palmitate and stearate are stored as triglycerides in fat cells or adipocytes. So we call the fat tissue adipose tissue, and the fat cells are called adipocytes, which means the cells of fat or fat tissue or adipose. The triglyceride is composed of a glycerol with three fatty acid chains. Again, we are going to talk about these in a separate chapter about lipids and triglycerides and fatty acids. But here just an overview of the oxidation of fat. So just remember, I know you already know this from your nutrition class, that a triglyceride is composed of a glycerol with three fatty acid chains, and these fatty acids can differ from each other inside the structure of a triglyceride. But we have two main fatty acids that our body can burn for energy is palmitate and stearate. Lipolysis is the breakdown of triglycerides. Again, just recall from previous lessons, uh, any term that ends with lysis, any word that ends with lysis, it means breaking down. And we have free fatty acids in the blood that bind albumin in the blood and taken up by muscles. And there, our muscles can use these free fatty acids to oxidize it and to use as a fuel source. Beta oxidation, it's a series of reactions that fatty acids must pass through before entering the Krebs cycle. And after entering the Krebs cycle and the electron transport chain, all those reactions are identical to the oxidation of carbohydrates. But before, it's like the beta oxidation is the preparation step or process. It's the preparation process of fatty acids to enter them to the Krebs cycle. And they are a series of reactions. It takes place in the mitochondrial matrix. So beta oxidation, unlike the glycolysis, which takes place in the cytoplasm, beta oxidation takes place in the mitochondria. And it's a process of four chemical steps. The overall function is to remove two carbon segments from fatty acid chains and convert them to acetyl-CoA. Remember, I said acetyl-CoA is a two carbon compound. So when we remove two carbon segments from fatty acids, those segments can be converted to acetyl-CoA. And from there, that acetyl-CoA enters to the Krebs cycle and do the rest of the process of oxidation. And it results in NAD and FAD just like the carbohydrates. And palmitate produces 113 ATP. That's why we get 9 kilocalorie per gram of fat. Because fatty acids, glucose was a like six carbon molecule, but fatty acids can be 16 carbon molecules or 18 carbon molecules. So that's why we get too much energy from burning fats. It's like 9 kilocalorie per gram of fat. Um, that's one of the reasons. That's one of the main reasons because they contain more carbon atoms than proteins and carbohydrates. And here, like palmitate, it produces 113 ATP. Regarding the oxidation of proteins, again, uh, the preparation process, the preparation phase is different from glucose, glycogen, and fatty acids. But after we get acetyl-CoA, the rest of the process is the same. We need proteins for like as enzymes, and they are called functional proteins. So when we refer to enzymes, they mean functional proteins. We have structural proteins. That's where we see in skeletal muscle. Proteins, unlike fats and carbohydrates, they cannot be stored as an energy source, so we cannot store proteins in our body to future use, unlike other macronutrients. And the building blocks of proteins are amino acids. For instance, the building blocks of glycogen is glucose. The building blocks of starch is glucose. And the building blocks of proteins are amino acids. And these amino acids can be metabolized aerobically. So we can oxidize amino acids to get energy from them. And in order to prepare amino acids to use as an energy source, we have to remove the amino group from the structure of amino acids. So amino group should be removed. And in order to remove the amino group, there are two different processes can be uh, can be occur to amino acids. The first one is transamination, and the second is deamination. In the transamination, it's the removal and transfer of a nitrogen group to another compound. In the deamination, the process of removing and eliminating a nitrogen group. That's the difference between these two processes. So in the preparation of proteins to use it in the oxidative phosphorylation energy system, we have to remove the amino group through these two processes, transamination and deamination. And the nitrogen, which is removed from the amino acids through deamination, is used to synthesize urea in the urine. So, and this picture shows the breaking down of macronutrients. As you can see, we have fats and proteins. So, lanine is one of the amino acids. Recall from your nutrition courses or biochemistry course, we have 20 different amino acids, and alanine is one of them. Alanine is a three carbon amino acid. We deaminate the alanine. So after the deamination, the alanine can be converted to acetyl-CoA. It produces one pyruvate and one acetyl-CoA. And isoleucine is another amino acid. It's a six carbon amino acid, just like glucose. So we get a three acetyl-CoA from isoleucine. Protein oxidation rarely exceeds 10% of total energy production. So we rarely use protein as an energy source. It's just 10% maximum. It's not more than that. And it most of the time it happens in starvation or in stressful conditions like chronic disease or different illnesses. That's where we get to burn more proteins. We oxidize proteins more than other in other conditions. But these are the main conditions where we burn proteins, starvation and stressful conditions. And here is the summary of all three energy system contribution over time. The red one is the ATP creatine phosphate energy system. The blue is the glycolysis, and the green one is the oxidative energy system. As you can see, over time, we use all these three energy systems. But in the like over time, like in the 5 minute, the oxidative energy system, we predominantly use oxidative phosphorylation energy system compared to other energy systems. But at the beginning of the exercise or physical activity, we use ATP creatine phosphate, which is 100%, almost 100%, but it decreases over the course of time and other energy systems become predominant. So at rest, the body uses carbohydrates and fats for energy. And during moderate to severe muscular effort, the body relies mostly on carbohydrate for fuel. Why are carbohydrates and fats preferred fuel sources compared to protein? What do you think about this? First, proteins are not stored for ready access, so we don't store proteins. Um, we store carbohydrates as glycogen and fats as triglycerides, but we do not store proteins. So that's one reason why we prefer our body, our cells prefer carbohydrates and fats for fuel sources. And the second step is in this, and the second reason is that additional steps are required to remove and dispose of the nitrogen group. So our body uses more energy if it wants to use protein as a fuel source because we cannot burn nitrogen groups. We have to get rid of them and we have to make a urea and then excrete it as urine. So our body needs more energy and more time. It takes too much work to do so. Which macronutrient can be metabolized aerobically for ATP production? Carbohydrates only, fats only, carbohydrates and fats, proteins only. Carbohydrates and fats. That's what we use most of the time for ATP production. The respiratory exchange ratio, it's very interesting topic to talk about. And this is the formula of the respiratory exchange ratio, RER, the respiratory exchange ratio. It is it's like a um, math problem, you know. It's V, like which is the volume or carbon dioxide production over oxygen consumption. That's the formula for the respiratory exchange ratio. And it indicates the utilization of carbohydrates and fat as fuels, the proportion of energy coming from carbohydrates and fats. This is what it shows, it indicates. It shows us like when we have the value for RER, we can say how much the energy comes from carbohydrates and how much of it comes from fats. That's what it says. That's what it shows us. And at rest, fat is the body's preferred fuel source, as we discussed. Fat and carbohydrates, but fat is more than carbohydrates. And under normal circumstances, at rest, fat is 85%. Carbohydrates make up only 15%. Excessive reliance on fat metabolism can cause some problems. It produces keto acids, which can disturb the acid-base balance in our body. Because it's acid, it can reduce the pH in the blood and it can cause metabolic acidosis, or this is the case what we see in diabetic ketoacidosis. Because people with diabetes, they are insulin resistance, they cannot use glucose as a fuel source, so they rely on fat metabolism. And from burning more fat, they can produce more keto acids, and that's why we call it ketoacidosis, DKA. DKA. One molecule of glucose is a 6 carbon sugar. It requires 6 oxygen molecules and it produces 6 carbon dioxide. So the respiratory exchange ratio is 1. So if we only burn glucose, the respiratory exchange ratio will be 1 based on the formula. And one molecule of palmitate, it's just 16 carbon fatty acids. it requires 23 oxygen molecules and it only produces 16 carbon dioxide. So if we divide this, the RER will be zero point zero 0.07. And RER above 0.90, it's common for moderate to hard intensity or moderate to high intensity exercises. So here is the percentage of carbohydrates and percentage of fat utilization based on the RER. So if RER is 1, we use 100% carbohydrates to, to produce energy, to produce ATP. And if we go down like in point 0.7, the percentage of fat is 100. So we use 100% fat to produce ATP. As activity increases, the body relies more on carbohydrates and less on fat. At fairly modest levels of physical activity, 50% from fat and 50% from carbohydrates. This is like 50% of energy is coming from fat and 50% of energy is coming from carbohydrates at fairly modest levels of physical activity. But whenever the level of physical activity increases, the body relies more on carbohydrates and less on fat. So RER increases as activity increases. At moderate to high intensity exercise, it's 100% from carbohydrate. And diet affects the distribution of fat and carbohydrate metabolism as well. If we consume high carbohydrate diets, our body relies on like burning more carbohydrates because we have plenty of them. And if we consume high fat diets, our body relies on burning and breaking down fats more than other macronutrients. So that's why these are the factors that affect fuel utilization. Diet is one of the important factors. Duration of physical activity, the intensity of physical activity, the athlete's training status. Higher trained athletes, they use more fat. We have a fed-fast cycle. The fed or absorptive state, it's a 3 to 4 hour period after eating. And the most important hormone in this state is insulin. And we have the post-absorptive state, which is the between the meal. Between the meal is fully absorbed, but before the next meal is eaten. And the fasting is 18 to 48 hours without food. The glycogen, which is the storage form of glucose, is depleted in the liver. And so when we have a depletion of glycogen, our body, especially in the liver, we produce glucose by gluconeogenesis. And amino acids as source of the glucose, the gluconeogenesis. And recall from our first lesson, lactic acid is also a source for gluconeogenesis. 18 out of 20 amino acids are glucogenic, means our liver can use 18 different amino acids to produce glucose through gluconeogenesis. Alanine, lactate, and glycerol in the liver, they are being used to produce glucose. And we have the starvation, which is the lack of food intake more than 48 hours. So Between 18 to 48, it's called fasting. And above 48 hours, it's called starvation. The brain cells use ketones in this state. And here it's the how different tissues use different macronutrients and energy and fuel in different states. So, for instance, our muscle use glucose for energy in the fed state. And in the starvation, muscle depends predominantly on fatty acids and ketones for energy. The central nervous system, like brain, in starvation, it depends primarily on ketones, but in other states, it predominantly relies on glucose. When total caloric intake constantly exceeds expenditure and carbohydrate intake constantly exceeds the body's need for immediate energy and glycogen storage, what happens? Carbohydrate undergoes a series of chemical reactions in which it is incorporated into fatty acids and stored in adipose cells. This is what happens to carbohydrate if we exceed the intake of carbohydrate but not burning them, not using them. Oxygen consumption. We have maximal energy consumption, and this graph shows that. So in the x-axis, we have exercise test stage and VO2 in our y-axis. So there is a linear relationship between exercise, test stage, and VO2. But after a while, it plates out, which we call it VO2 max. So in this VO2 max, it's just a vertical, it's not a vertical, it's not a horizontal line, and we cannot exceed that VO2 because it's the maximum. We cannot like exceed that. That's called VO2 max. Our body cannot use more than that, more than like that level. And this VO2 max is different from person to person. It depends on many different factors, like genetic factors, gender. So this is different. So it's like it doesn't mean that, for example, if the VO2 max is 65 milliliter per kilogram per minute, it can be 70 for another person, can be 55 for another person. So VO2 max can be different from person to person. But just remember that there is a linear relationship, but later it plays out. Now we have submaximal energy consumption, submaximal oxygen consumption. If exercise intensity is below the person's maximal ability, it's called submaximal. It's like below maximal ability. And here in this part, there is a lag in oxygen consumption at the onset of exercise, which is called also oxygen deficit. That's like where exercise starts. So there is a lag in oxygen consumption. And here in this part, we have a gradual decline in oxygen consumption after exercise. It is also called excess post-exercise oxygen consumption, EPOC. Why is there a lag time in the rise in oxygen consumption at the onset of exercise? Why do we have this lag here at the beginning, at the onset of exercise? What do you think? Well, at the onset of exercise, our body relies on an aerobic energy system, which are independent from oxygen. That's why there is a lag in oxygen consumption at the beginning, at the start of exercise or physical activity. And also, this is called oxygen deficit state or oxygen deficit period. And the factors that influence the maximum oxygen consumption, as I said, there are different factors, and the VO2 max is different from person to person. But nutritional status, specifically iron status, can influence the maximum oxygen consumption. Genetics, gender, age, and exercise training, like how athletes train their energy systems can influence the maximum oxygen consumption, and the habitual physical activity can also increase the VO2 max. Let's talk about the alcohol metabolism really quickly. You remember from your chemistry class that alcohol is also called ethanol. It can absorb in the stomach, and its absorption is very rapid, regardless of having food in the stomach or not. The absorption is rapid, but with food, it gets slower. But overall, the absorption rate of ethanol in the stomach is very rapid. We get 7 kilocalorie per gram of alcohol, of ethanol. And when we say moderate alcohol intake, it means up to 1 drink per day for women, up to 2 drinks per day for men. And when we say like 1 drink or 2 drinks, these are the serving sizes or serving equivalents. It's like half an ounces or 14 gram of ethanol, which equals to 5 ounces of wine, 10 ounces of wine cooler, 12 ounces of beer, so on and so forth. So these are all like 5 ounces of wine is 1 drink, 1 drink alcohol. The alcohol metabolism takes place in the liver. Other tissues are not capable of using alcohol or metabolize alcohol. Only liver can metabolize alcohol. And there are two pathways for alcohol metabolism, which depends on the amount of alcohol consumption. In the presence of alcohol, the breakdown of ethanol is the priority. So our body prioritize the alcohol metabolism because it's like it's a toxic compound to our cells. So the liver prioritize the breakdown of ethanol in the presence of alcohol. So there are, as I said, there are two pathways. So in low to moderate levels, in low to moderate intake of alcohol, we have alcohol dehydrogenase pathway ADH, which occurs in the cytoplasm of the liver cells. This pathway is called alcohol dehydrogenase. The second pathway is the microsomal ethanol oxidizing system. It takes place in the microsome. Microsome is another organelle inside the cytoplasm. And the enzyme in the microsome is which is responsible for the alcohol metabolism is called cytochrome P450. And this enzyme sometimes, some medicines can inhibit the activity of this enzyme. That's why they say, okay, do not drink alcohol if you take this medicine, because that medicine inhibits cytochrome P450. So the liver is not is not able to metabolize alcohol, and that can cause some dire consequences to our body, es- especially to the liver. Is ethanol capable of being converted to fat and stored in adipocytes? What do you think? This is for your own. You can go and search and learn more about this. So this was all about our last lesson for chapter 3.